Hello everyone. Today we are going to talk about mother of all dragons. Nope, sorry. That would have been cool though. But we are going to talk about something more cool perhaps. Mother of all 2D motions. The cyclist doing his morning routine or the moon doing its weird dance around the sun while the earth is orbiting the sun. Yes, this motion has a fancy name and it's called the curvilinear motion. So, what is this curvilinear motion anyway? Well, it is any particle traversing a given path, a curved path. Let us study this motion. But what do we mean by studying the motion anyway? Well, it just means that you should be able to tell the position of the particle, or the velocity of the particle, or its acceleration at any given instant of time with respect to a frame of reference. Well, so we invented a frame of reference, which literally means the coordinate systems. One of the coordinate systems that we are extremely familiar with is the rectangular coordinate system. Since our high schools, it consists of an x-axis, a y-axis, and the other name of this coordinate system is the Cartesian coordinate system. And the coordinates of the point are referred to as the ordinate and the abscissa. Ordinate essentially means the distance of the point from the x-axis, the perpendicular distance, and abscissa means the perpendicular distance of that point from the y-axis. The other coordinate system that is also used is the polar coordinate system, where the coordinates of the point depend upon the distance from a reference point and the angle from a reference point, from a reference direction. The third coordinate system that we are going to focus more upon in this video is the normal and tangential coordinate system. And as the name suggests, the coordinate system uses the position of the particle in space as the origin, and the tangential axis is drawn in direction of the instantaneous velocity, and the normal axis is perpendicular to the tangential axis. The particle traverses along the path, the whole coordinate system shifts with it. Since the direction of instantaneous velocity is changing all the time, the tangential axis also changes, and thus the normal axis. Now we can move on and see why this specific coordinate system is so useful for dealing with curvilinear motion. Here, a doubt may arise in our minds that there are many versions of perhaps normal and tangential axis that can be drawn at a specific point, two of which cases are shown in here. Well, the rules go as follows. The tangential axis has to be drawn in direction the particle is moving, and the normal axis has to be drawn such as it points towards the center of curvature. Don't worry with all this bombarding of new terms. We will get to the center of curvature in a short while. One of the ways to study this curvilinear motion is to formulate its acceleration. Acceleration is defined as the rate of change of velocity with respect to time. But what is this velocity vector anyway? Velocity vector is just the magnitude, that is the speed, times the direction, that is in the direction of the tangential axis. So what is dv by dt then? To find this, we need to employ the product rule of differentiation. After employing this product rule, we get dv by dt is equal to dv by dt ut plus v times dut by dt. In the right-hand side of this equation, there are two terms, out of which dv by dt simply means the change in speed with respect to time. The other mystery of this equation is the dut by dt. Let us find out more about that. So what is ut dot, you ask? Well, look at this geometrical representation where ut represents the unit vector along the tangential axis, un represents the unit vector along the normal axis, and ut dash is the unit vector that represents the changed tangential axis after an instant of time. By vector analysis, we can see that dut vector is the change in ut vector. And how to find this dut vector? The answer is differential calculus.
Let's look at the concept of curvature. We'll be considering these 2 points on our path. The angle between tangents to these points or t-axis to these points is delta theta. Now this a bit weird looking definition of curvature simply means delta theta divided by delta s, which is the length of the path between those 2 points over a very small interval of x, which simply means k equals d theta by ds. Now to actually get the expression for k, we use a little bit trick. We multiply it by dx by dx, which is essentially 1. Now let's look at how this helps us in getting the expression for k. Let's find out dx by ds first. Going back to our graph, we'll zoom in a little bit and discover that due to the fact that dx is very small, we get this nice simple right angle triangle, which means we can use Pythagoras theorem to get the value of ds. Now, looking at our goal, we'll express ds in a slightly suitable format, which will easily give us the value of dx by ds. Now let's find out d theta by dx. The same right angle triangle and a bit of trigonometry will help us get the value of d theta by dx. Now, here differentiating d theta and using the chain rule, we get this value for d theta by dx. So now, multiplying these two factors, we get the value for k. But wait, there's more. K is also defined as 1 divided by the radius of curvature, which gives us this very useful and simple relation r equals ds and d theta. Now let's see how this helps us in simplifying our physics problem.
So here we are again with our geometrical representation, and after gaining a ton of mathematical knowledge to solve this physics problem. Now we know that ds is equal to r d theta and dut is equal to ut times d theta. Therefore, dut vector is equal to ut times d theta in the direction of the normal axis. Now, since the magnitude of ut is unity, we have dut vector is equal to d theta in the direction of normal axis. We also know that d theta is equal to ds by rho, where rho is the radius of curvature and has this humongous formula which my friend explained and I lazily would not repeat. After manipulation and a bit of rearranging of the terms, we have dut vector as ds by rho in the direction of normal axis. And therefore, the dut vector by dt is v by rho in the direction of normal axis. Now, this is the mystery term from the right-hand side of the equation of acceleration. After substituting this value in that equation, we get acceleration as dv by dt in the direction of tangential axis plus v times v by rho in the direction of normal axis, thus concluding that acceleration has normal component too. Voila!